Hey everybody, good morning. Um, Again, sorry I'm not able to be there with you, but I think you guys took some prayer requests and prayed this morning. Just wanted you guys to know that I'm praying for you as well. Um, I miss you guys and wish I could be there, but wanted to let you guys know that I'm actually flying out of the country. I'm going to Eurasia, um, actually to a portion of Central Asia this Wednesday, and I'll be gone for about 4 or 5 days. We're going to be celebrating a distribution of scriptures in sign language for the first time, and a people group that have never had scripture before. There's about 1.4 million deaf people there. So please be praying for that time. God's going to do some really, really great things, and we're just so excited to be a part of that. But please be praying for that. I leave on Wednesday and come back the following Monday. I think Miss Barabo has given you back your homework. I've made notes on there. If anything's unclear, please feel free to email me. I also handed back the quizzes and wanted to just say a couple of kind of overall comments about the quiz. It sounded like there might have been some confusion. It sounded like time might have also been an issue. There's a couple things I want to say to that. First, I just wanted to, it sounded like some people had some questions about number 2 on the quiz. So if you've got your quiz, go ahead and pull it out. Take a look at number 2 there. I'm pulling it out myself here. So it said, draw an example of a function on the interval from 0 to 4 that has an absolute max but no local max, no absolute minimum, and no local minimum. Okay. So one of the things to remember, we kind of talked about this before. We did talk about this before, and then I think I reviewed it the time that Miss Barabo was kind of sitting in on the class. But it sounds like this is a point of confusion. So I am going to, when we do review for the exam today, I am going to go through some more of this. But just so it's clear, one of the things we talked about was if you have an absolute max or min, then one of two things is happening. That's either a local max or min, or it's an endpoint. So if you remember, what's important here is are the definitions. So an absolute max and min, and again we'll go over this, but an absolute max or min, that is the highest point on the graph, just bar none. Doesn't matter where it's at on the graph, it's just, if there's a highest point, that's the absolute max. If there's a lowest point, that's the absolute min. A local max or min means it needs to be defined in an open interval around the point. So it can't have nothing on one side or nothing on the other side. So the issue, endpoints are issues here. You can't have a local max or a min if it's trying to happen on an endpoint. So in other words, if I had something like this is going to be a problem in a second, I'll fix this, but this is, right now, the way this is drawn, this is my absolute max, but it is not a local max, okay? Because there's nothing defined on the right side. That was our issue with absolute max and local max, okay? So that's what I was looking for that part on number 2. You wanted no absolute minimum, so there's actually a couple of different ways that you could do that. You could have this thing come down like this and have an open circle and then stick a point up here. Several of you just had this open and nothing, it wasn't defined at 0. I actually need a function from 0 to 4, so it needs to be defined everywhere. So you might have seen me put a dot on your graph. The other thing that can happen is I can just have like a vertical asymptote of some kind. So it can do something like this. This does not have an absolute minimum either. Okay? So that was the kind of thing that I was looking for. And when we do the review, we'll get into some further details. One of the other things that I noticed on the quiz was that several people were doing some kind of interesting cancellation. I saw things like this. Like one of the fractions had an x squared plus 4 down here on the bottom, and people were factoring this. Like x minus 2 and x plus 2. Those are not equal. Okay, you can't factor x squared plus 4 using real numbers. You can't do that. X squared minus 4 factors this way, but x squared plus 4 does not. So I saw a few people doing that. In particular, I think on number 3, you end up with, when you do a derivative, you end up with this fraction, okay? Whenever you've got a fraction that's in fairly, this is not too complicated now, you immediately need to ask 2 questions. Where does this not exist, and where does it equal 0, okay? When you're looking for where does it not exist, you're looking in the denominator. The denominator is defined everywhere, so there's no place where this does not exist. If you're looking for where the derivative equals 0, then you want to set the top equal to 0. You don't care about the bottom. Okay, you want to set the top equal to 0. Don't worry about the bottom. And then in this case, you end up getting plus or minus 2. Square root of 4 is plus or minus 2. Okay? And then you plan out your stuff from there, etc. All right? Okay, I think that that was sort of overall. Maybe one other time I saw somebody do this. I think you had some sort of derivative that looked like this. And then somebody canceled that with one of those. Please don't ever do this. This is like a huge no-no in math. This is kind of like scraping your fingers on a chalkboard for a math professor. Please don't cancel like this, because you're trying to cancel a factor of x squared plus 4, but there's an x. You haven't dealt with this term that should also have an x squared plus 4. Don't do that. Okay? Be super careful. That people can get upset about that. All right? So I think that covers questions on the quiz. You can obviously redo homework for full credit within the next week. You can redo your quiz for half credit. I want to give you the opportunity to be able to do that. I did want to also say that I know it feels like there's some time constraint on the quiz. There's actually a reason for that. You need to be able to do these problems in a reasonable amount of time, in part because the stuff you're doing now is giving you a tool to be able to do other things later. And if you allow yourself to just kind of take a long time doing this, then that's going to make doing the stuff that this is a tool for, it's going to make it even more long and complicated. So you need to get proficient and familiar with this stuff enough that you can do it under not an unreasonable time constraint. I'm not expecting you guys to just crank this out, but you do need to be able to do it with a little bit of speed and be able to maintain that accuracy. Okay, so if you want to, we should today be able to get through what we need to. You'll have time to work on homework. You'll have time to work on redoing some of this stuff too. So if you want to hand this back to Miss Baribeau and with corrections, and she'll get those to me, and then I can correct those. So the plan for today, the plan for this week, is today we obviously have class. We're going to review for the Chapter 3 exam. We've only got 5 sections from that exam, from Chapter 3, but our test on Thursday, it's actually Thursday morning, starting at 8, is just going to be from those 5 chapters. It's not cumulative, doesn't go back to the beginning of time. Obviously, you need to know things like derivatives and other stuff to be able to do that. But then Thursday is going to be the exam. Next week, just as a clue in, Monday there's no school, and then Tuesday is Monday classes. So we're actually going to next week have class Tuesday, Wednesday, and Thursday back to back, boom, boom, boom. so you're going to want to, we're going to be going over Tuesday and Wednesday, we're going to be talking about curve sketching, which is kind of bringing everything together so far from section 3.5, chapter 3. And then, so that's Tuesday and Wednesday, and then Thursday is optimization. So these are all applications of derivatives. So that's the next several weeks. Today what we're going to do is we're going to review chapter 3. And like I said, this shouldn't take the whole time. And then you should have plenty of time to be able to work on the finish up 3.5 homework if you haven't done that to turn in today. Work on the review problems and then any corrections that you have that you want to turn in. Just so you know, the answers for the section 3.5 problems are on RenWeb, and the answers for chapter 3 review problems are also on RenWeb. If you guys want me to actually directly email them to you, I can. Just email me and let me know, and I can send you that file. So that can kind of be a tool to study with while you're working on those homework problems. Hopefully that will help. Okay? So let's review. So this is chapter 3, section 3.1 through 3.5. All right. So starting with section 3.1. So this was, the main topic of this was absolute and local, or absolute and relative maxes and mins. So the first thing that you ended up getting introduced to was absolute maxes and mins. What are they? So you need to understand the definition. I'm not going to have you quote the definition on an exam, but you do need to understand the definition. This is just the absolute highest and the absolute lowest point on the graph. You can have multiple ones. So this can happen in multiple places, but the highest y value, there's only one, and the lowest y value, there's only one. And the y values are called the absolute max or the absolute min values. Okay, when we use the word values, that means y value. Okay, these together are called the extreme values. And so then we had a theorem which was called the extreme value theorem. And what this said is if you have a continuous function on a closed interval, that forces the function to have an absolute max and an absolute min. If you remember, we went through lots of examples where on a closed interval, you don't have to have an absolute max, you don't have to have an absolute min. You could have vertical asymptotes, the thing could come down, have a circle, and then jump up. So we're not always guaranteed to have an absolute max or min. But if you have a continuous function on a closed interval, that does guarantee that you have an absolute max or an absolute min. Okay. And so then we have the definition of local or relative max and min. Okay. The key here is that it needs to be in an open interval where the function's defined. It needs to be the highest point or the lowest point on some open interval where the function is defined. And this was exactly the issue we were just talking about before with endpoints. If you have an endpoint that appears to be a local max or a local min, the problem is that if you go past that and take an open interval, it's not necessarily the highest or the lowest point on that interval because you don't have anything to compare it to on that one side. So you cannot have local maxes or mins at endpoints. You can have absolute maxes or mins at endpoints, just not local maxes or mins. So then you should expect me to give you problems kind of like what you saw on number 2, where I'm asking for can you have an absolute max that's not a local max? Give me an example. Or can you have a local max that's not an absolute max? Or can you have an absolute max that's an absolute min? Is that possible? What's going on with the function when that happens? Can you have, a local max that's also a local min? Something like that. So be thinking about the relationships between those. It'd be very easy for me to give you an example or to ask you to give me an example or give you kind of a true-false question, something along those lines. Okay? So you're going to want to be able to compare absolute and local maxes and mins. Okay, you're going to want to be able to compare those. Okay, so now the point of this section was really how do we know when we have absolute maxes and mins, and then how do we find them? And so the way that we found them, we used something. We actually looked at the fact that an absolute max or min is actually a local max or min, or it's an endpoint. And so then we said, okay, well, so if we want to find absolute maxes and mins, what we need to do is look for local maxes and mins and endpoints. How do we find local maxes and mins? Well, it turns out the local maxes and mins are in places where either the derivative there is 0 or the derivative does not exist. Okay, and so we gave this a special name. If you have a place in the domain where the derivative equals 0 or does not exist, we gave this a special name. We called these critical numbers. Okay, so you need to remember what is a critical number. The only thing that people tend to get messed up on, as long as you remember derivative is 0 or derivative doesn't exist, the only thing that people tend to forget is that critical numbers have to be in the domain of the original function. You can't have a place where that's a critical number, but the function's not defined there. It has to be defined there, okay? So, for instance, 1 over x, the derivative doesn't exist at 0, but the original function doesn't exist at 0. So 0 is not a critical number for 1 over x. So you have to be careful that you're actually talking about points that are in the domain of the original function, okay? So types of questions I could ask you for something like this. Here's a function, find the critical numbers. There were homework questions that were kind of like that, okay? And so then finally from section 3.1, section 3.1 is actually the longest one, we had the closed interval method. Okay, the closed interval method was kind of our method for finding the absolute max and min of a continuous function on a closed interval. Okay, if you remember here, what you do is you find the critical numbers and the endpoints, and then you list them all and plug them into the function. The highest point is the absolute max, the lowest point is the absolute min. So that is the closed interval method. So if I say, here's a function, use the closed interval method to find the absolute max and min of this function on this interval, you need to find critical numbers and endpoints, make a list, and plug them all into the original function. Don't plug them into the derivative, plug them into the original function. Okay? All right, so that's section 3.1. Like I said, 3.1 was the longest. It had a lot of stuff that it was introducing. Okay. So now we go to section 3.2. Section 3.2 was really just two main theorems. It was Rolle's theorem and the mean value theorem. So you need to remember the conditions of Rolle's theorem. So you need to remember the conditions here. We need a function that's continuous on the closed interval and differentiable on the open interval. And the function at the two endpoints has the same value. So f of a equals f of b. Those are the conditions on Rolle's theorem. And then the conclusion is that there has to be a place in between that we called C where the derivative is 0. Okay, that was Rolle's theorem. All right. Then we had the mean value theorem. Okay, and again, you need to know the conditions here. The conditions are the same as for Rolle's theorem. It needs to be continuous on the closed interval, differentiable on the open interval, but here the two endpoints don't have to have the same y value. And then the conclusion is different here. The conclusion is that whatever this slope is, there has to be a place where the derivative is the same as that slope. So the formula that we had is that f prime of c equals f of b minus f of a over b minus a. Okay, that was our mean value theorem. And we had a couple of applications of the mean value theorem and of Rolle's theorem. We looked at things like we said, for example, if you probably remember the speed problem that we had. If you're driving to Detroit and you're going 200 miles and you get there in 2 hours, on average you were going 100 miles an hour. Were you going exactly 100 miles an hour at any one point? And then you can prove that yes, you actually were. You can prove this using the mean value theorem. The mean value theorem it relates the function to its derivative. So if I think I remember another problem that I gave you that was an example was if you know that f of 0 is like 3 and the slope never gets any bigger than 2, then how big can f of 4 be? So you can use the mean value theorem to say, no matter what, the derivative, there's a place in between 0 and 4 where the derivative is f of 4 minus f of 0 over 4 minus 0. And you know how big this gets, and you know how big this is, so that gives you an estimate on f of 4. So the mean value theorem relates the function to its derivative. Okay? I won't go crazy with applications there, but you do need to know the statement of the mean value theorem, the statement of Rolle's theorem. You should be able to draw a picture. And then a couple of basic types of applications. Okay, so that's section 3.2. The other three sections are actually going to fly because there's not a lot that's going on in those. You've actually been using those a lot. Okay. Section 3.3 is just on increasing and decreasing. Okay, so local maxes and local mins. So you need to be able to answer the question, if I give you a function, where is that function increasing and decreasing? Okay, you take the derivative. This is standard stuff that you're used to doing. You take the derivative. You find where the derivative does not exist or is equals 0, and then you check points around. The places where the derivative is positive, it's increasing. The places where the derivative is negative, it's decreasing. Okay, so this is where you draw your number line and you're looking at pluses and minuses there. And then you use that information to answer the question, where does the function have local maxes or mins? Okay, so again, if you have your number line drawn, like if you figured out that the derivative is 0 at 1 and does not exist at 3, I'm just making something up here. And then this is plus, plus, and minus. You can see where the function's increasing and decreasing, and then right here, there's a local minimum. There's no local maximum. Okay? That's section 3.3. The place where you tend to get hung up on this stuff, I think, is taking the derivative, figuring out where it does not exist or where it equals 0. It's more of the algebra of the thing than anything, right? Okay, section 3.4 is kind of the same thing, but it's on concavity, so we're talking about the second derivative now. So we ask the question, where is the function concave up or concave down? So here you do the same thing you were doing with the first derivative, but you do it with the second derivative. So where does the second derivative not exist or equal 0? Checkpoints around. If it's positive, it's concave up. The function's concave up. If it's negative, the original function is concave down. Okay, you do need to know what concave up and concave down look like. Increasing and decreasing, I think you were already familiar with, but concave up, concave down means curved up and curved down. Okay, and then where are the inflection points? Okay, the two things that you need to remember here, okay, if I had, let me draw a number line here. So let's say it's at 2 and 5. The second derivative is 0 at both of those. And the second derivative was plus, plus, and minus, so we're concave up, concave down. First of all, there's really three places where people get caught up here. Inflection points are only places where the concavity changes. So right here, 2 would not be an inflection point. You could not have an inflection point at x equals 2. You would only have one at x equals 5. So it has to change concavity. The second thing that people don't realize or they forget is that the function needs to be continuous at an inflection point. It's not an inflection point if the function is discontinuous. It can change concavity, but if the function's not continuous there, it's not an inflection point. So the function needs to be continuous. In particular, sometimes people will say there's an inflection point where the function's not even defined. Don't do that. Like if this was D and E, if the original function wasn't defined and it was curved up here like a vertical asymptote and then curved down, that's not an inflection point, okay? The third point that people, forgive the pun, but the third point is that an inflection point has to be a coordinate. It's x comma y. It's never just, I have an inflection point at x equals 2. Don't write that. Okay, because if it's an inflection point, you have to write the point. So it has to be 2 comma whatever. To find that y coordinate, do not plug into the derivative or the second derivative. Please, please go back and plug into the original function. Okay? So that is concavity. And the last section that we can have on the quiz, or sorry, on the exam, is section 3.5, and this is limits at infinity. And so this is when you see a limit as x goes to infinity or a limit as x goes to negative infinity. A couple things to remember. So first of all, if x is going to infinity or negative infinity, and you have a constant over x to a positive power, that always goes to 0. This is a key thing that we use. So like 5 over x squared, if x goes to infinity or negative infinity, that thing goes to 0. Okay, so that's the first thing to remember. Second thing to remember is that when you're faced with something that's a lot more complicated, our typical rule is we divide the top and the bottom by the highest power of x Sorry, my computer shut off here. We divide the top and bottom by the highest power of x on the bottom, okay? And you've seen a number of examples of that now on the homework. Again, the solutions for the homework, Ms. Barabo has them. I posted them on RenWeb. You see most of those examples. I'm looking on the bottom, find the highest power of x, divide by that. If the highest power of x is under a square root, don't forget that it's effectively half of the power. So if it's an x squared, but it's under the square root, the highest power is effectively x on the bottom, that kind of thing. Okay. And then the last thing to remember is that there's a couple of tricky things that happen. So if you're looking at a square root, then like if there was an x squared plus 5 on the bottom, and so x squared under the square root is effectively x. If I were to divide that square root by x, I want to bring that x into the square root. But in order to do that, I have to make the x into a square root. That works if x is positive, I can make it x squared of x squared. But if x is negative, if I square it and take the square root, I killed the minus sign, so I have to artificially reintroduce that. So in other words, if you're looking at a limit as x goes to infinity, infinity means we're a really big positive number, you use this. If you're letting x go to negative infinity, you're a negative number, so you need to use this. Okay, so that's just a little intricacy to remember in the case that you're doing one of these limits. Now, the reason you would do these limits is that you would be looking for horizontal asymptotes. Okay, you see me abbreviate these HA. Okay, remember that a function can only have at most 2 horizontal asymptotes because you're looking at what happens when x goes to infinity, what happens when x goes to minus infinity. So if somebody says, where are the horizontal asymptotes for your function, you should always look at 2 limits. You should look at the limit as x goes to infinity of the function and the limit as x goes to negative infinity of the function. Okay, if that ends up going to a number, that y equals that number is the horizontal asymptote. All right? So that is a review of what you're going to see on the exam on Thursday. You've got some questions from the chapter that I've given you out of the book. Ms. Barabo is there to answer your questions too. If you've got further questions after class and want to email me, that's fine. Otherwise, we will see you on Thursday, and it's Thursday, I believe it's Thursday at 8 a.m., and I will definitely be praying for you guys. Even I'd probably be somewhere in Moscow at the time. So I'll be praying for you guys, and I appreciate your prayers for me and the work that's going on there as well. Thank you guys so much. God bless, and take some good time to get your practice in.